In this video, we're going to look at how glycolysis is regulated. So we need to go back to the idea of flux control that we talked about in a previous video. And flux, if you remember, is just like how much stuff, or in this case glucose, is flowing through glycolysis. And so under steady state conditions, glycolysis operates continuously in most tissues. It's always going on. What's changing is just how fast it's going. So this flux has to change based on the needs of the organism. And flux control, seeing what enzymes or what mechanisms are involved in flux control, that is, what are the actual dials to speed up flux or slow down flux, are based on three things. One, identify the rate determining steps of the pathway. To do that, you need to know delta G in vitro. The enzymes that are far from equilibrium are going to be your control points. After you've found your control points, determine the allosteric modifiers of those enzymes. And then measure the in vivo levels of the regulators under various conditions to see if the concentrations change, that is, if your flux is changing consistent with your proposed control mechanism. So just recap: 1, what reactions are far away from equilibrium? 2, what can change the rates of these enzymes? 3, if I change the rate, is the overall flux change? Do I speed up glycolysis or do I slow down glycolysis in the cell? Alright, so if we look at delta G for all of our reactions, you will notice that 3 are far from equilibrium. That's reaction 1, reaction 3, and reaction 10. And we can look at the delta G's as this chart showing the energies, and you can see the giant drops off. Those are our control points. This is where we propose the flux of metabolism, that these enzymes, these 3 enzymes, will determine the overall flux. Everything else near equilibrium, they will equilibrate quickly. They are very sensitive to changes, but the 3 target ones, that's where if we change those, then those are going to be a big change in our flux. Alright, so hexokinase in your skeleton muscles, which is the first reaction, you actually don't really need that. We don't do that reaction in your muscles all that much. And that's because in your muscles, glycogen is going to be the source of glucose. And when you break down glycogen, if you remember from Biochemistry 1, glycogen is just glucose linked together as storage. What you do is when you break it apart, you make it into G6P. You don't make it into glucose and then G6P. You directly make it into G6P. So we never use hexokinase, so that's not the major control point for glycolysis. Pyruvate kinase, which was delta G negative 13.9. This is the last step, so really wouldn't make sense to regulate glycolysis at the very last step. So the contender is PFK, which is step 3. Delta G, very negative, 25.9 kilojoules per mole. And indeed, PFK is very elaborately regulated. Like the hemoglobin we looked in Biochemistry 1, this has R and T state, R for on, T for off. It's tetrameric, has 4 subunits. ATP is its substrate, but it's also its inhibitor, which makes sense. Glycolysis, you're trying to make ATP, so if you have a lot of ATP around, stop doing glycolysis so much. So ATP will bind as an inhibitor only in the T state. So if ATP binds in the inhibition area, then it's going to force the T state. ADP, AMD, and fructose 2,6-bisphosphate reverse this inhibition and forces it into the R state. So those are our allosteric regulators right there. Alright, if we look at the speed with ATP and AMP, you can start to see how these regulators work. So no inhibitors, low ATP activities, incredibly fast, even at low amounts of fructose 6-phosphate. If you add ATP with some AMP, The rate's slowing down now because you've added ATP. However, if you compare the red and the green with and without AMP, with AMP it's still faster than without AMP. So what this is telling you is that high concentrations of ATP slow down your mechanism, your enzyme. However, AMP speeds it up because I'm comparing the green and the red lines here. Without AMP, ATP is just completely slowing down this enzyme. Alright, so let's see how this mechanism works. So we're looking at the enzyme binding pocket for F6P here. T state is blue, R state is red. So the R state happens when you bind F6P, which makes sense because that's your substrate. So if you bind that, you want to be active. What happens is that arginine 162, so here's the T state arginine 162, it swings all the way over to F6P. And now you have this salt bridge or positive negative interaction happening. In the T state though, this 162, like I said, is all the way over here. And in its place, glue 161, which was right here, swings into that binding site. So in the T state, you have a negative charge right here. So F6P won't want to bind because it'll be negative repulsion. So that is how the T state is preventing your substrate from binding, by putting a big negative glutamic acid right where the negative F6P wants to bind. But if you bind ADP, this actually inhibits the T state from forming. So ADP right here will stabilize the R state. And you can see in the T state here we have an amino acid 150 that will swing out of the way, go all the way over here, which will swing arginine all the way into the binding pocket, and it will swing glutamic acid away from the binding pocket. So ADP will actually favor the R state as well. Or sorry, favor the R state, prevent the R to T transition. Now, let's look at some of this allosteric regulation. I know there's a wall of text here, but just stay with me and let's walk through this. So, we saw in the previous chart about kinetics that PFK is allosterically regulated by ATP. And so you might think to yourself, oh, that's easy. Glycolytic flux is completely controlled by ATP. That's it. And it makes sense. If ATP levels are high, PFK is inhibited, flux is lowered. If ATP is low, flux is high, ATP is made. And flux can change 100-fold. So you can 100-fold the amount of ATP you can change just by regulating PFK. Think of PFK as your dial, or on your faucet, go to high flow, low flow. However, the levels of ATP in your cell, in your muscle cell especially, between rest and vigorous exercise never really changes more than 10%. It stays relatively the same. And we actually talked about this on a previous video. ATP is buffered via creatine kinase and adenylate kinase. This enzyme has this reaction. Two ADPs make ATP plus AMP. The ratio between ATP, AMP, and ADP squared is 0.44. And these enzymes will make sure that this ratio is always 0.44. So there has to be more complex mechanisms to explain how our flux can change just by 100-fold. Can't just be the amount of ATP, because ATP doesn't change that much. We would expect bigger concentration changes. Well, another information that we looked at is that AMP and ADP actually relieves this PFK inhibition by ATP. AMP will bind to the R state of PFK. ADP binds to the R state of PFK. So it stops any inhibition. And the reason why this is, and why this is the mechanism for our control, is that in your muscles, ATP is 10 times more, the concentration is 10 times more than ATP, and the concentration is 15 times more than AMP. And what that means, by thinking about that this ratio always has to be 0.44, if you decrease your ATP by 10%, this results in a 100% increase in ADP and a 400% increase in AMP. So it's not so much that a decrease in ATP is speeding up your cells, or your PFK rather, and speeding up flux. It's that a decrease in ATP increases ADP and AMP a lot. So by just turning one dial down 10%, you turn two other dials up 100 and 400%. So it's your ADP and your AMP that are interacting with your PFK. The PFK goes to the R state. PFK is the main control point for glycolysis, so when it's on the R state, it will speed up glycolysis. However, that is not the full picture either. There's additional control to PFK, which is a good thing because this is making energy for us, making ATP. We want to make sure we can control this enzyme very well, because we don't want to get into a situation where we have too much ATP or too little ATP. And if you remember when we were talking about flux, we said there's one way we can change flux in a reversible reaction. We can either speed up or slow down the forward reaction, or speed up and slow down the reverse reaction. These things, messing with these, will change the overall flux of a pathway. However, for PFK, the reverse is negligible. It is not reversible. It only goes in one direction. This is not the case, though, if we want to go in the reverse pathway, if this is actually carried out by a different enzyme. If different enzymes do this reverse reaction, then VR is no longer negligible, because you're doing a different pathway, which could make this a spontaneous reaction. And the enzyme that will do this reverse pathway is called fructose 1,6-bisphosphatase, or FBPase, important in gluconeogenesis. This is in all your tissues, and this catalyzes our reverse reaction. FBP plus H2O makes F6P plus PI. And what we're doing is called substrate cycle. So our substrate cycle is right here. So we go G6P and we make F6P. We take this X6P and make FBP, burns in ATP. We take this FBP and using a different enzyme, we chop the phosphate off and go to F6P. You can see this is a cycle that's just using ATP and doing nothing. So originally these were called futile cycles because people thought you're just wasting ATP and not doing anything. There is regulatory function for this though. You can affect this reverse reaction and speed it up or slow it down. And you are producing a big effect on flux if you do that, than if you just sped up or slowed down one pathway. In reality, you're not changing the maximum flux, right? So just imagine that this reverse pathway wasn't here. You could speed up this pathway and you could reach a maximum. It doesn't matter if this one's here. You're just going to reach a maximum no matter what. The important thing is that you're decreasing the minimum flux. By having a secondary enzyme here, you're more or less saying, I can only go so slow. Because, let's say you're not exercising. You're just doing this futile cycle right here. Your glucose that has gotten in this part is in a holding pattern. It's already gone through the first couple of steps of glycolysis, and it's just waiting to go down the line. So let's say that you're at rest and then you do some exercise. Well, you don't want to have to break down a bunch of glucose, move it into glucose 6-phosphate, move it to fructose 6-phosphate to start going. It's nice that you already have a pool here ready to go. And that's what's being shown here. So we shut off the reverse enzyme. Now all of our flux is going downhill because we're not remaking anything. So we have increased the flux, but in this holding pattern, we're making sure, okay, we're ready to go as fast as possible if we need to. like I say here, allowing for a rapid change from resting to high activity. And this cycling is usually under hormonal or neuronal control. And this substrate cycling is actually important when it comes to obesity. And it's also important when it comes to body heat. So one way body heat is mainly generated is through substrate cycling in the muscle and liver. You're doing a fetal reaction to produce heat. This is called non-shivering thermogenesis. Your thyroid hormone takes care of this. It stimulates metabolism in most tissues. So non-shivering thermogenesis and metabolism are linked. And there's been experiments that in rats, if you remove their thyroid gland or make a non-functioning thyroid gland, they can't survive at 5 degrees C or lower. They're not making enough internal body heat. And chronically obese individuals, they usually have lower than normal metabolic rates. And if you have lower than, well, this is partly due because you have reduced rates of non-shivering thermogenesis. You're not doing these fetal cycles, so the minimum flux of metabolism is lowered. Your overall metabolism is lowered, so it's hard to get to your normal states. And these individuals are also cold sensitive because you're not making enough body heat. While normal weight humans and animals will increase thyroid hormone activation on exposure to cold to speed up this non-shivering thermogenesis, obese animals and obese humans don't do this. So they are cold sensitive, they're not creating enough body heat, and that's lower than normal metabolic rates. So that's just a health connection, one of many, to what we've been talking about in humans. And thank you for your attention. I will see you in the next video. That's all for this one.